Welcome back to DeepVisus, where vision meets depth. I'm your host, and in this episode, we're diving into two fascinating chapters from Neural Fields, Theory and Applications, edited by Stephen Coombes, beim Graben, Roland Potthast, and James Wright. Today, we'll explore chapters 8 and 9, both centered around the role of noise in neural fields. How does noise influence the dynamics of neural activity, and what new behaviors emerge from incorporating randomness into neural field models? That's the question we'll seek to answer today. Let's get started. Chapter 8, titled Heterogeneous Connectivity in Neural Fields, a stochastic approach, introduces the idea that real neural networks are far from homogeneous. In traditional models, neural fields have assumed that connectivity is uniform across the system, meaning every neuron interacts with others in the same way. But in reality, neurons can have varying connection strengths. This chapter takes us into the world of stochastic inhomogeneity, where connections are not uniform but are instead randomly varying. The authors explore two types of inhomogeneity. 1. Local inhomogeneity, where connection strength varies over short distances. 2. Long-range inhomogeneity, where connections extend over larger distances between neurons. So, how does this randomness affect the neural field? The key finding is that the introduction of stochastic inhomogeneities leads to two main results. Persistent fluctuations in activity, meaning that instead of settling into a stable state, the neural activity keeps fluctuating. Fluctuating traveling fronts, where the movement of wavefronts across the network is no longer smooth or predictable but varies in speed and shape due to noise. The chapter shows that these fluctuations are influenced by factors like the strength of connections and the level of inhibition in the system. For example, increasing the strength of inhomogeneity leads to more synchronized fluctuations across the network. The authors also introduce a new concept, persistent fluctuations, a behavior not previously observed in deterministic neural field models. These fluctuations are essentially random oscillations in neural activity that can persist indefinitely even without external input. This idea has important implications for understanding how working memory and spontaneous activity might function in the brain, where activity needs to be sustained over time. Now, moving on to Chapter 9, titled Stochastic Neural Field Theory, we dive even deeper into how noise influences neural networks. The chapter is centered around synaptic noise, which arises from the random inputs neurons receive from each other. These random fluctuations can have profound effects on how neural fields behave at the population level. The chapter covers both extrinsic noise from external sources and intrinsic noise from internal neuron fluctuations. The author, Paul C. Bresloff, builds on earlier work and explores how to extend mean field theory to incorporate synaptic noise. By doing so, he shows that when noise is included in the model, we observe two key phenomena. 1. Fluctuating wave fronts, where traveling waves of neural activity no longer move uniformly but fluctuate due to the randomness of the network. 2. Rare transitions to extinction, where, due to noise, the system can eventually reach an absorbing state where all activity dies out. But how can we analyze these noisy systems? Bresloff introduces a path integral formulation, a powerful mathematical tool to describe the most likely paths the system takes toward extinction. This approach allows us to understand the dynamics of neural fields under stochastic conditions, such as how noise might cause a system to move from a stable state to one of complete activity extinction. So, to answer our initial question, how does noise affect the behavior of neural fields? Both chapters illustrate that stochasticity, or randomness, fundamentally alters neural dynamics. It introduces persistent fluctuations, wandering wave fronts, and rare transitions that are absent in deterministic models. These behaviors could have significant implications for understanding how the brain operates under normal and perturbed conditions, especially in processes like memory and sensory integration. In conclusion, noise is not merely a disturbance, it plays a central role in shaping the behavior of neural systems. By incorporating randomness into neural field models, we can better capture the complex, fluctuating nature of brain activity, making these models more realistic and applicable to real-world phenomena. And that's a wrap for today's episode of DeepVisus, where vision meets depth. We've learned how stochastic neural field theory opens up a new understanding of neural activity driven by noise and fluctuations. But what happens when noise is not just external but also generated within the network itself? Stay tuned for our next episodes, where we'll explore this question further and continue unraveling the mysteries of the brain through neural field models. Thanks for listening, and see you next time.